let's look at one more example where we're going to stay just in spherical coordinates, but we're going to get an idea of how that can be a little more useful. So in this first video, we're going to look at the first two parts, and in the next video, we're going to look at the final part. So for all parts, we're given this vector field D, which is defined as shown here, r sine of phi in our r direction, 1 over r sine theta cosine phi in our theta direction, and r squared in our phi direction. And we want to determine the following. So first in this video, we're going to find the value of our vector D at some point, which is given as 10, 150 degrees, 330 degrees. And we're going to see that's as simple as just plugging in values. And then second, we want to find the component of D tangential to the spherical surface r equals 10 at point P from part 1. So let's get started. So in our first part, we just want to find the value of D at point P. So literally all we're doing is just plugging in values. So let's come down here and say for 1, we want to find that value. So our D, our vector field, is now equal to, so we plug in 10 for r, and then we plug in for our phi and theta as well. So now r, and so which one is which? Of course we know that this is r, this is theta, and this is phi. So for our phi value, we're going to plug in our 330 degrees, and that is in our r direction. We then had minus 1 over r, so r was 10, times sine of theta, theta was 150, and times cosine of 330, that was in our theta direction. And then finally in our phi direction, we had r squared, r is 10, that's multiplied by our unit vector in phi direction. So evaluating all of that, we get that our D at point P is approximately -5 in our r direction, minus 0.0433 in our theta direction, plus 100 in our phi direction. And so that would be our answer for part 1. So really just plug and chug. Now, our second question is a little more conceptual. We have to think about this a little more. So we want a component of D tangential to the spherical surface r equals 10 at point P. So we're going to be using this answer from part 1 here, and we're saying when that D is evaluated at point P, we want the part of that that's tangential to a spherical surface. Okay, well, let's take a step back and sort of talk about how we can decompose vectors. So it turns out that any vector can always be decomposed into a tangential and a normal component. So any vector can always, so always in terms of, it doesn't matter what coordinate system we're in, if we're in spherical, cylindrical, Cartesian, we can always take this vector and resolve it into two components, or decompose into two components. And so the key thing is that these two components are going to be orthogonal or perpendicular. So we can say, for instance, if we're talking about D, at any point we can say that is D sub t plus D sub n. And so what these two components are, our D sub t is our tangential component, and this is at a given surface, and our D sub n is our normal component. And then let me just say here, to given surface. So both of those apply to given surface. So it's tangential component to a given surface, normal component to a given surface. So what we're talking about here is a spherical surface. So not a great artist, but let me just roughly, so we've got a circle here, and then of course it's sort of 3D, so we have something that looks like this. And we're saying that this is r equals 10. So it's a sphere with radius 10. So at this point, D, which is -5 in r direction, 0.043 in our theta, 100 in our phi, which corresponds to this point here. Sorry, that previous thing was our vector value. So it corresponds to this point here. We want the component of that that is tangential to our spherical surface. So our spherical surface, if we notice we have a sphere with r equals 10, then if we have a constant r value, our r unit vector is always going to be perpendicular to that surface. So here, this surface, so if I just sort of shade that, I know that makes it difficult to see. Let's say that surface is r equals 10. Our u of r is going to be perpendicular. So we can say, perpendicular, so u sub r is perpendicular to our r equals 10 surface. And so what we can do then is we can use sort of this basic equation here, and we can say that our d sub n is equal to -5 times u sub r from our previous equation. So our previous answer, we found that we had a -5 in our r direction, so that's going to be our normal component. So now if we want our tangential component, we can say d sub t is equal to d minus our normal component. So just rearranging this equation here, we can find our tangential component. And so that turns out to be the two remaining components, so our theta and our phi component. So -0.0433 in our theta direction, plus 100 in our phi direction. And so that would be our answer for part 2. So I know that was a little bit rough towards the end, so if you do have any follow-up questions, or if you want to see that figure drawn a little more accurately in terms of the point and the direction, let me know and I can try to help you visualize that a little better.